Hello everyone, I am Honar Cook, a PhD scholar at IIT Kanpur. Today I will solve the previous week's problem and week 12 problem also. And if you have any doubt, you can ask me. And this will be the last problem solving session for this course. So we will solve first problem. What would be the correct order of increasing operational Mach number and decreasing specific impulse for the following propulsion unit? There are four options: turbojet, which comprises of turbojet, turboprop, ramjet, scramjet, and rocket. So what will be the answer for this problem? So in that class you might have seen this plot where specific impulse and flight number are plotted together. And let's say for this hydrogen fuel, there is this turbojet, ramjet, and scramjet, and rocket engine. So initially at low Mach number, this turbojet is used, and when Mach number reaches till about 3, then at that time ramjet is used. Then between 3 to 6, this scramjet is used. Ramjet is used between 3 to 6. At Mach number 6, around Mach number 6, we use the scramjet. And the limit of scramjet is not tested, but it is assumed that till Mach number 15, it will give good specific impulse. After that, due to the high Mach number and chemical reaction, this specific impulse will decrease lower than rocket. So this will be the correct order. So first we will use the turbojet, then ramjet, then scramjet, and then rocket engine. So option C is the answer. We will see the next problem now. When performing compressive boundary layer computation on a flat plate, the following engineering technique provides a very close match with the exact solution using a simple and economic solution technique. Option A, Blassi's equation. Option B, Reynolds analogy equation. Option C, Prandtl's boundary layer equation. Option D, reference temperature method. So what will be the answer for this? Its answer will be reference temperature method. So generally, if you solve for compressive boundary layer for let's say chemical reacting mixture or viscous flow, there are very we need high computational power, and also it is very complex. So generally we use the implicit formula for let's say CF and CH Stanton number and local skin friction coefficient. These formula we use for implicit, and in this formula we replace rho by rho star, T by T star, and mu by mu star. And this T star is the reference temperature, which is present at some point in the boundary layer. This point can be anywhere, and at this temperature we calculate the density and viscosity, which is given by rho star and mu star. And then for the calculation of these properties we use all these parameters. So then if you check, then you will find that these results are very much near to the viscous solution. Only slight, it will be slightly lower than that, but that error is very low. So that's why we use the reference temperature method. We'll see the next problem. When performing computations on a hypersonic entry vehicle geometry, the following is or are applicable. There should be a fine mesh deployed around the body to resolve the boundary layer. Option B, for viscous flow computations, continuity equation with mass diffusion, Navier-Stokes equation, and energy equation, including conductive and radiative heat transfer, would have to be computed with variable fluid properties for continuum flow regime. Option C, species concentration equations have to be included in the numerical model. Non-equilibrium chemistry model has to be included in the numerical model. So which of these options are true? You can read it and tell. So we'll check all these options one by one. So first option, there should be fine mesh deployed around the body to resolve the boundary layer. So the mesh should be fine, and to check the mesh we also do one grid independent study. So in this grid independent study we try to make finer and finer mesh and check at what mesh, after what mesh the flow is not changing, flow properties are not changing. Then use that mesh for the computation. So this statement is true. Option B, for viscous flow computation, continuity equation with mass diffusion, Navier-Stokes equation, and energy equation, including conductive and radiative heat transfer, would have to be computed with variable flow properties for continuum flow regime. So first thing is that this Navier-Stokes equation works for continuum flow regime only, so we will use for continuum flow regime. And for viscous computational, we know that we need continuity equation, momentum equation, energy equation. In continuity equation, we will also include the term for mass diffusion, because mass diffusion also happens when there is change in concentration. And in energy equation, we will include both conductive and radiative heat transfer. And there are various flow properties like viscosity, thermal conductivity. These flow properties and this mass diffusivity. So all these flow properties we will use as a variable flow properties. So these properties will change with temperatures. So this statement, if you see, this is also a true statement. Often see, species concentration equations have to be included in the numerical model. As there are multiple species, then we have to use species concentration equation also. This is also true. And oftenly, non-chemistry equilibrium chemistry model has to be included in the numerical model if tau c is approximately equal to tau f. This tau c is the chemical reaction time and this tau f is the flow time. When this chemical reaction time and flow time are of the same order, then the flow will be non-Euclidean. So if flow is in non-Euclidean, then we have to include the non-Euclidean chemistry model. And what is the equation? That one equation will be the vibrational relaxation, vibrational rate equation, and other will be the chemical rate equation. These both equation we have to include. So this is also true statement. So for this problem, all four options are correct. Is there any doubt? If no, then we will see the next problem. Arrhenius equation is used in defining rate constant in high temperature air involving chemical non-equilibrium. The rate constant can be written in the following form. Epsilon A is the activation energy. Option is C e to the power kT upon epsilon A. Option B C e to the power minus kT upon epsilon A. Option C e to the power minus epsilon A upon kT. Option D C e to the power minus EA epsilon A upon kT square. So if you remember the Arrhenius equation, you can directly tell which is the correct option. So what will be the correct option for this problem? Okay, so correct option will be, so rate equation is given by k equal to C e to the power minus epsilon A upon kT. These two k are different. This k I will let k be here, Boltzmann constant. And this k is rate constant. So correct option will be option C. Now we'll see the next problem. Shock wave reflection and shock interaction phenomena can be represented effectively using option A velocity altitude map, option B pressure deflection diagram, option C Mollier chart, and option D theta beta diagram. So what will be the correct answer? The correct answer for this is pressure deflection diagram. So we'll see what is a pressure deflection diagram. Let's say there is one bed with an angle theta, and there is one shock. Due to this shock, their pressure from P1 to P2 is changed. And where Mach number is m1. So if this is theta and this is pressure P and this point is P1. So for a Mach number m1, you can draw one curve. This is not, I have not made properly, but it is somewhat like this only. For Mach number m1, we can draw one P pressure deflection diagram, but this will be for theta max. So if it is like this. uh, so this will give the value of pressure at different angle. So let's say angle is theta, then this will be the P2 value. And you can see that each theta has the two values of pressure. So one is for weak shock and one is for strong shock. So this P2, we get this P2 for this theta angle. So like this we can find. Now let's say if there is one pipe and there is two wedges here with angle theta 1 and this will angle theta 2. So there will be shock interaction, like there will be one oblique shock here, one oblique shock here, and due to their interaction there will be one flip line, and this will be the transmitted shock. So this theta, this is theta 2 and this is theta 1. So if you see this diagram for P1, here preferably P1 M1. So for P1 this diagram will be like this, and we can get for this theta 2 which is positive we will get this pressure, and theta 1 which is negative we will get this pressure. This was made for M1. Let's say here Mach number is M2 and here Mach number is M3. So for Mach number M2 and theta 1 we will make one more diagram, theta P diagram, and for this also we will make one more diagram. So like this, these two are meeting here. So this will be the final flow angle. This will be the angle of the flow, which is phi. So like this we can solve what will be the end pressure and what will be the deflection angle. Like this it is very easier to solve the shock wave reflection and shock interaction phenomena using the pressure deflection diagram. Now we'll see the next problem. M infinity equal to 10 airflow past a flat plate will be option A frozen for an inviscid flow, option B equilibrium flow for a viscous flow if tau f is very greater than tau c. Tau f is the flow time and tau c is the chemical reaction time. Option C non-equilibrium flow for a viscous flow if tau f is approximately equal to tau c, and option D air will behave as a calically perfect fluid within the boundary layer. So what option will be the correct option? So we will check each option one by one. Let's say this is the flat plate. If there is flat plate and flow is inviscid, there will not be any boundary layer. So flow will directly pass through it. So the flow will remain frozen. So option is correct. Now let's say viscous flow is there. Then for the viscous flow there will be boundary layer. And if tau F is greater than tau C. It means flow time is very greater than tau C, chemical reaction time. Then it means the flow will reach the equilibrium flow. So it also satisfies the condition. This statement is also correct. Option C, if both are of the same order. Flow time and chemical reaction time are both are of the same order, then the flow will be non-equilibrium. So this option C is also correct. And if you see the option D, it says the air will behave as a calorically perfect flow within the boundary layer. This is, you can say this is the wrong, because what will happen that let's say this for Mach number 10 inside the boundary layer, its kinetic energy will be changed to thermal energy. So due to this thermal energy, the temperature will be high. So this high temperature, due to this high temperature, there might be vibrational and chemical non-equilibrium which can be present in the system. So, or there might be chemical reaction also. So it is not for it. So due to the chemical reaction, species concentration can also change. And even if there is no chemical reaction, the temperature might be sufficient high for the value of Cp and Cv to change with respect to temperature. So air will not behave as the calorically perfect fluid within the boundary layer. So this option is wrong. So option A, B and C are correct. Now we'll see the next problem. Lewis number deals with option A, inertia force and viscous force. Option B, conductive heat transfer and radiative heat transfer. Option C, energy transport caused by diffusion relative to thermal conduction. Option D, energy transport caused by advection relative to conduction. What will be the correct answer? Okay, so first we'll see what is the Lewis number. Lewis number is given by LE. So LE equal to rho E T12 E. This E is for edge of the boundary layer. So you can directly write this here. This L equal to rho T12 Cp upon K. So you can see in the numerator it depends on the diffusion. Numerator takes the term for diffusion and denominator takes the term for thermal conductivity. So you can say this is caused by energy transport caused by diffusion relative to thermal conduction. So option C is the correct option. Now we'll see the next problem. Viscous reacting air at hypersonic flow conditions involves molecular transport phenomena of the following kind. Option A, mass. Option B, energy. Option C, momentum. Option D, bulk viscosity. First thing to note is that what will be the answer for this problem? So first thing to note is that this bulk viscosity is not any transport phenomenon. So this option will be wrong. Due to the mass, there is transport phenomenon which is called diffusion. So mass diffusion happens due to the concentration gradient. Due to the energy, there is conduction happens, thermal conduction. It is due to difference in temperature, or you can say energy. And due to difference in momentum, there is one phenomena which is gives viscosity. So all these three are, and diffusion is related to diffusion coefficient. And this is also under thermal conductivity. Okay. Diffusion coefficient is given by D and viscosity by mu. So all these three are related to molecular transport phenomena. So option A, B, C are correct answer. Now we'll see the next problem. Choose the correct option in the context of physical properties of viscosity, thermal conductivity, and diffusion. Statement 1. In non-reacting viscous flows, only viscosity and diffusion are important. Statement 2. In chemically reacting viscous flows, viscosity, thermal conductivity, and diffusion are important. Option A. Statement 1 false. Statement 2 false. Option B. Statement 1 false. Statement 2 true. Option C. Statement 1 true. Statement 2 false. Option D. Statement 1 true. Statement 2 true. So what will be the answer for this problem? So first, for non-reacting viscous flow, if there is non-reacting, then you can say that density of different species is not changing. So there will not be gradient of the species. So diffusion is not that much important. Only important is viscosity and thermal conduction. So statement 1, which says about diffusion being important and thermal conduction being not important, is false. Statement 2 says, in chemically reacting viscous flows, viscosity, thermal conduction, and diffusion are important. So in chemically reacting viscous flow, the concentration of each species will change. So due to the change in species concentration, the diffusion will also become important. That's why in chemically reacting viscous flow, all three, viscosity, thermal conductivity, and diffusion, are important. So this statement is true. So which is the option which is correct? If statement 1 false, if statement 2 true. which is option B. So option B is the correct answer. Now we'll see the next problem. Kinetic theory equivalent for a perfect gas equation of state is given by option A, PV equal to 2 by 3 E translational mole, where E translational mole equal to 3 by 2 RT. R is the universal gas constant and T is the temperature. PV equal to 2 by 3 E translational total, where E translational total equal to 1 by 2 sigma I mi vi square. Mi is the mass of ith particle and vi is the velocity magnitude of the same particle. Option C, PV equal to 2 by 3 E translational 1, where E translational 1 equal to 3 by 2 RT. R is the specific gas constant. PV equal to 2 by 3 E translational 2, where E translational 2 equal to 3 by 2 kT, where K is the Boltzmann constant. So first thing to know that E translational mole is 3 by 2 RT per mole, and this R is the universal gas constant. So per mole energy of the gas is given by 3 by 2 R by T, translation energy. So we can also write PV equal to 2 by 3. If we see from option A, E translational mole, and if we put this 3 by 2 RT here, then we'll get RT. So PV equal to RT is nothing but perfect gas equation. So these equations are same. So option A is the correct option. Option B says PV equal to 2 by 3 E translational total. Now if we see the E translational total translation energy will be the sum of total kinetic energy of the particles. So sum of, if you put the sum of, so the two, this part was already correct. This total energy PV will be equal to total energy, and this total energy will also be given by half sigma I mi vi square. These both are correct. That's why this option B is also correct. And option C and D are wrong. One thing to know that it is not mentioned what is this 1 2 E translational 1 2. So we cannot say if this will be equal to 3 by 2 RT or 3 by 2 KT or not to satisfy the perfect gas equation. That's why only option A and B are the correct option. Now we will see the next problem. Pressure exerted on the walls of a vessel due to molecular collision of the particle of a perfect gas contained in it is given by mi is the mass of the ith particle, vi is the magnitude of the ith particle, vi is the magnitude of the velocity of the ith particle, and v is the volume of the vessel. So option A is P equal to sigma I mi vi square. Option B, P equal to V sigma I mi vi square. Option C, P equal to 1 by 3V sigma I vi mi square. Option D, P equal to 1 by V sigma I mi vi square. So what will the answer for this problem? If you see from previous problem, we got that PV equal to 2 by 3 heat translational total. We got this from kinetic theory of gases only, and which consider the molecular balance of the particle with the vessel. And we also got that heat translational total is nothing but 1 by 2 sigma I mi vi square. If we substitute this here, then what will we get? PV equal to 1 by 3 sigma mi vi square. And if we take this v to other side, then we get P equal to 1 by 3v sigma I mi vi square. This will be the pressure. So which option is correct? Option C is the correct option. Now let's see the next problem. Choose the correct option in the connection with Fock standard distance for a calorically perfect gas, air assumption, and equilibrium high temperature air. Chemical reactions in high temperature air increases ρ2 by ρ1, which reduces the Fock detachment distance. Statement 2. The Fock standard distance for calorically perfect air assumption is less than Fock standard distance for equilibrium high temperature air. Of statement 1 true, statement 2 false. B. Statement 1 false, statement 2 true. C. Statement 1 true, statement 2 true. Option D. Statement 1 false, statement 2 false. So in this problem, we are asked that for which case Fock standard distance will be high or low, for calorically perfect gas or chemically reacting gas, equilibrium chemically reacting gas. So which of the option will be correct? So before that, we will see what happens to density across a Fock. Actually, this is for normal Fock. This is for normal Fock. And if there is one normal Fock, then just after the Fock, there will be thin region, very thin region, which will have frozen flow. This will be for frozen flow. And frozen flow behaves like a calorically perfect gas. After that, there will be some small region which will be for non-equilibrium flow. And after that, flow will be in equilibrium. So across a Fock, temperature and density increases. And this initial, just after the Fock, this value will be equal to frozen properties, or you can say similar to calorically perfect gas. But if you see the temperature inside the Fock layer, the temperature will be high. So due to this temperature, the there are chances of vibrational non-equilibrium and chemical non-equilibrium. So due to this non-equilibrium, uh, some of the energy will go to vibrational mode and some will go to the for dissociation of the gases. So due to the dissociation of the gases, this temperature will decrease, or some energy, the translation energy will be consumed. So as temperature is mainly gained by translation energy, the temperature of the gas reduces. So inside the non-equilibrium region, the temperature of the gas will reduce, and it will reduce till we attain the equilibrium. So when equilibrium is attained, temperature will remain constant. Now, as rho is inverse proportional to temperature, if temperature is decreasing, then density will increase. So density will increase inside the boundary layer, soft layer, and it will increase till we attain the equilibrium. Now, as the density has increased, so let's say this similar thing will happen for the Boson also. So let's say this is the body and this is the Boson. So before density was, let's say, rho 2 1, and later this rho 2, this is rho 2 calorically perfect gas, and 1 is rho 2 equilibrium. So this rho 2 will be less than equilibrium rho 2. So as for the equilibrium, rho 2 will be high. Then for the same mass flow rate to pass through, the shock layer should decrease. So shock standoff distance should decrease. So that's why shock standoff distance delta for equilibrium will be less than shock standoff distance for calorically perfect gas. Or you can say, for the, if let's say there is one sphere of radius r, then its shock standoff distance is approximately given by 1 upon rho 2 by rho 1. And as we already seen, rho 2 by rho 1 for equilibrium will be higher than rho 2 by rho 1 for calorically perfect gas. So if this is rho 2 by rho 1 is higher, then it means that shock standoff distance is lower. So for the equilibrium flow, shock standoff distance will be lower than the calorically perfect gas. So statement 1 says, chemical reaction in high temperature air increases rho 2 by rho 1, which reduces the shock detachment distance. We already saw that if there's chemical reaction is happening, then rho 2 by rho 1 will increase, so which will reduce the shock standoff distance. Statement 2, shock standoff distance for calorically perfect air junction is less than shock standoff distance for equilibrium high temperature air. The first statement is true, which we saw. And second says the shock standoff distance for calorically perfect air junction is less than shock standoff distance for equilibrium high temperature air. So this also we saw that for equilibrium, shock standoff distance will be less than for calorically perfect gas. So this statement is false, because it says that for calorically perfect gas assumption, shock standoff distance is less, which is untrue. So which of the option is correct? It is option A, which says statement 1 true and statement 2 false. Now we'll see the next problem. connection of fork standoff distance del scaled with respect to radius of curvature of a sphere r ahead of which the fork is approximately formed is given by often a del upon r is approximately equal to under root rho 2 upon rho 1. Often we del upon r is approximately equal to 1 upon root 2 by rho 1. Often C del upon r is approximately equal to 1 upon under root rho 2 by rho 1. And D del upon r equal to root 2 by rho 1. So what will be the answer for this problem? So in the previous problem itself, we saw that del y r is approximately equal to 1 upon rho 2 by rho 1. So in the previous problem, we saw that del y r is approximately equal to 1 upon rho 2 by rho 1. So option B is the correct option. Now we will see the next problem. Electrical conductivity of high temperature viscous reacting air becomes important in studies involving option A astrophysical flows, option B viscous reacting air at 4000 Kelvin at 1 atmosphere pressure, option C viscous reacting air at 10,000 Kelvin at 1 atmosphere pressure, option D magneto-hydrodynamic flow. What will be the correct option for this problem? So electrical conductivity becomes important whenever there is involvement of electron. So when electrons becomes involved, when there is astrophysical flow or when there is ionization. And ionization happens for air when its temperature is greater than 10,000 Kelvin and at 1 atmosphere pressure. And magneto-hydrodynamic flow. So for all these cases, the electrical conductivity becomes important. So option A, C and D are correct option. Option B says that viscous reacting air at 4000 Kelvin at 1 atmosphere pressure. At that temperature there is no ionization, so electron ion will not be present. So this electrical conductivity is not that important. So option B is wrong. Now let's see the next problem. In binary mixture of two gases M and N, the mass flux of species M, that is the mass diffusion of M per unit area per second, is given by Ci is the mass fraction of the species I, dKe is the diffusion coefficient for species K into species E. Option A is the Fick's law. Option B, Jm bar equal to minus rho dnm del Cn. C, Jm bar equal to minus rho dnm del Cm. Option D, Jm bar equal to minus rho dmn upon del Cm. So we already know that mass diffusion is given by Fick's law, so option is correct. And one thing to note that if direction of del Cm, if we are finding the mass diffusion of species M, then we have to consider the concentration or mass fraction of gradient of mass fraction of species M only. So gradient of, if let's say gradient of mass fraction is in this direction, then diffusion will happen in opposite direction. So there will be one minus sign and diffusion will be direct to this del Cm. So Jm vector is equal to minus rho dmn. This dmn gives the diffusion coefficient of species M into species M. As diffusion is happening for species M, that's why we have taken dmn. So that's why option B will be wrong. And we have seen that diffusion is directly proportional to del Cm. So it will be del Cm. So this will be the correct option equation. So option C is the answer. And option A also. Option D will be wrong because del Cm is inversely proportional to mass diffusion. Now we will see the next problem. In a binary gas mixture containing two species A and B, two different experiments are conducted to compare the binary diffusion coefficients in the two cases D1 and D2 respectively. The experimental conditions are T1 equal to 4000 Kelvin, P1 equal to 4 atmosphere, T2 equal to 5000 Kelvin, and P2 equal to 3 atmosphere. Assume all other conditions are identical for both experiments. Option A 48 upon 125, option B 96 upon 125, option C 144 upon 125, option D 24 upon 25. Which option will be the correct option? So in this problem you have to solve it. So you can say that there are two cases D1 and D2. You have to find ratio of D1 and D2. D1 and D2 are nothing but diffusion coefficient for two cases 1 and 2. So T1 is given at 4000 Kelvin, T2 is 5000 Kelvin, P1 is given as 4 atmosphere and P2 is given as 3 atmosphere. So we have to find ratio of D1 and D2. Try to find it. So okay, now we will try to solve this problem. So first we have to see what is the equation for diffusion coefficient, binary diffusion coefficient, and it is given by, let's say, DAB is given by KAD, one coefficient, under root T upon sigma n, where n is the number density. And we know that P equal to N kBT, where kB is Boltzmann constant, so we can write N equal to P upon kBT. We will substitute this N here. We will get DAB equal to KAD under root T into kBT upon sigma P. KB and KAD both combined can be written as K dash AD T to the power 3 by 2 upon sigma P. So if we wanted to write equation for T1 upon T2, it will be written as T1 upon T to the power 3 by 2 and P2 upon P1 to the power 1. So if you put the values, we will write this here. T1 upon T2 equal to T1 upon T to the power 3 by 2 P2 upon P1. T1 is 4000 Kelvin, T2 is 5000 to the power 3 by 2, P2 is 3 and P1 is 4. So all these 0 will cancel to each other. And it will be equal to 9 into 4 upon 4 into 4, or we might write like this. This 4 to the power 3 by 2 will be 8. 8 into 3 upon 4 into under root 125. Before we cancel here 2, it will be 6 upon under root 125. So its answer will be 6 under root 25. These all options are wrong here. We'll see the next problem. Intermolecular force in the Leonard-Jones model is given by F equal to minus d phi upon dr. The function phi is given by epsilon is the characteristics energy of interaction between the molecule, and d is the characteristics molecular diameter, r is the distance. Often is 2 epsilon d upon r cube minus d upon r whole square. B, d upon r 12 to the power 12 minus d upon r to the power 6 upon 4 epsilon. Option C, 4 epsilon d upon r to the power 12 minus d upon r to the power 6. Option D, 4 epsilon d upon r to the power 6 minus d upon r to the power 3. If you remember the formula, you can answer this question. What will be the answer for this? If you remember that this Leonard-Jones model is also called 12-6 Leonard-Jones model. So these two often are directly wrong, you can see. Only often possibility of correct is for B and C. So now we'll see that a one force field is defined for the interaction of the molecule, and which is indicated by F, and according to Leonard-Jones model, F equal to minus d phi r upon dr, and this d phi r is given by 4 epsilon d upon r to the power 12 minus d upon r to the power 6, which is called Leonard-Jones 612 potential. So this will be the correct answer, which matches with option C. So option C will be the correct answer. Now let's see the next problem. Choose the correct option in connection with the thermal conductivity and binary diffusion coefficient. Statement 1. Thermal conductivity for a pure gas depends on temperature and number density of gas particle. Statement 2. Binary diffusion coefficient depends on temperature and number density of gas particles. Statement 1 A, first true. Statement 2 false. Statement B, option B, statement 1 true, statement 2 true. Option C, statement 1 false, statement 2 false. Option D, statement 1 false, statement 2 true. So what will be the answer for this problem? So for binary diffusivity, first thermal conductivity. Thermal conductivity is given by formula Kk under root T upon sigma. So from this formula you can see that it is dependent on only temperature, not number density. So the option statement 1 says that it depends on both temperature and number density, which is false. And if you see the binary diffusion coefficient, which is given by D, is given by KAD equal to under root T upon sigma n. This formula we have seen before, this one. So this we can see that it depends on number density and temperature both. And if statement 2 also says that it depends on temperature and number density. So this is the true statement. So option, which option will be correct? Option D, which says if statement 1 false and statement 2 true. Now we'll see the next problem. Number of thermal degree of freedom associated with the translational kinetic energy of the center of mass of a diatomic molecule is or are. Option A 1, option B 2, option C 3, option D 4. So that is one diatomic molecule, and we have to tell how many degree of freedom are possible for translational kinetic energy of the center of mass. So what will be the answer? Let's say there's one Cartesian coordinate on the center of mass x, y, z. Then you can see that this molecule can move in x direction also, y direction also, and z direction also. So it will have 3 degrees of freedom. So the answer for this problem will be option C, 3. So we'll see the next problem. The number of thermal degree of freedom associated with the rotational kinetic energy of H2O is or are option A 1, option B 2, option C 3, and option D 4. So what will be the answer for this problem? So as this is it has 3 atoms. So we have to check the structure of this molecule, and the structure of H2 is like this. Now if you draw one coordinate system here, then this atom can rotate about this y-axis like this, and x-axis like this, and z-axis like this. As all 3 rotations have some meaningful rotational energy, that's why total 3 number of degree of freedom are associated with rotational kinetic energy. So answer for this problem will be option C 3. Whenever there are more than 2 atoms are present in a molecule, then it is better to see the structure of that atom first. If the structure of atoms is in the straight line, then only 2 degree of freedom will be associated with it. Rotational degree of freedom will be associated with it. If it is not linear, it is non-linear like H2O, then there will be more rotational degree of freedom. Let's see the next problem. The number of thermal degree of freedom associated with the rotational kinetic energy of a diatomic molecule like N2 and O2 is or are option A 1, option B 2, option C 3, option D 4. Just now I have told about it. So what is the answer for this problem? So it is a diatomic molecule. So there are 3 axes, x, y, z. So it can rotate about y-axis, it can rotate about z-axis, but if it is rotating about x-axis, then its rotational kinetic energy will be very less, because all the mass are concentrated on this x-axis only. So that's why there will be only 2 degree of freedom associated with the rotational kinetic energy. So answer for this problem will be option B, 2. Okay, let's see the next problem. Maximum thermodynamic probability for bosons and fermions and J star are given respectively by here E equal to e to the power alpha, e to the power beta epsilon J dash. Often A equal to Gj upon E minus 1, Gj upon E plus 1. Often B E plus 1 upon Gj, E minus 1 upon Gj. Often C Ej plus 1 upon E minus 1, Gj plus 1 upon E plus 1. Often D Gj upon E square minus 1, Gj upon E square plus 2. What will be the answer for this problem? Okay, let's see. For bosons, the number of particles in jth energy level is given by Nj star equal to for the case of equilibrium Gj upon E epsilon e to the power beta epsilon J dash minus 1, and this e to the power epsilon beta e to the power alpha e to the power beta epsilon J dash it is nothing but E, so it can also be written as Gj upon E minus 1. Similarly, for fermion, this value is given by Gj upon E to the power alpha e to the power beta epsilon J dash plus 1, and this e to the power alpha e to the power beta epsilon J dash is nothing but E, so it is given by Gj upon E plus 1. So which option will be correct option? It will be option A, Gj upon E minus 1 for bosons and Gj upon E plus 1 for fermions. Now we will see the next problem. 4 important chemical reactions are stated below, which are relevant to represent the composition of high temperature equilibrium chemically reacting air in the temperature range of around 2500 Kelvin and 9000 Kelvin at 1 atmosphere pressure. O2 gives 2O, N2 gives 2N, N plus O gives NO, and N plus O gives NO plus E minus. The number of unknown partial pressures of various species involved in the above chemical reaction is option A 5, option B 6, option C 7, option D 8. So what will be the answer for this problem? So first we have to see how many species are present here. First is the O2, second is the O. O is present here also, here also. Third is the N2, fourth is the N, which is present here also, here also. Fifth is the NO, sixth is the NO plus, and seventh is the U minus. For total species present in the chemical reaction is 7. And each species will have their own corresponding partial pressure. So which will be PO2, PO, PN2, PN, PNO, PNO plus, and E minus. For total 7 partial pressure will be corresponding to 7 species, and all 7 will be the unknown partial pressure. So the number of unknown partial pressure of various species in the chemical reaction is how much? 7. So option C will be the answer. Now we'll see the next problem. Identify whether the following two statements are true and false. Statement 1. At very low temperatures, the Fermi-Dirac statistics and Bose-Einstein statistics are distinct or different. Of statement 2. At high temperature, there is no difference between Fermi-Dirac statistics and Bose-Einstein statistics given the Boltzmann limit. Option A. Both statements are false. Option B. Both statements are true. Option C. Statement 1 is true and statement 2 is false. Option D. Statement 2 is true and statement 1 is false. So it is about the Fermi-Dirac and Bose-Einstein statistics. So which one is the correct option? So if we have to tell the difference, if there is difference between Fermi-Dirac and Bose-Einstein statistics or not, at very low temperature and at very high temperature. So at very low temperature, less than 5 Kelvin, the most of the molecular system will be in the ground state. So these states will be heavily populated, and as these will be heavily populated, then there will be big differences between Fermi-Dirac statistics and Bose-Einstein statistics. But at high temperature, the molecule will be distributed over many energy levels. And as they are distributed over many energy levels, then their states are sparsely populated. Which means Mj will be very less than Jv. The number of particles in Jth energy level will be very less than the degeneration of the Gh level. Due to which what will happen if you see these equations? So what will happen? Fl to the power e to the power alpha, e to the power beta, epsilon j dash minus 1 will be value as greater than 1, and e to the power alpha, e to the power beta, epsilon j plus 1 will also be very greater than 1. So we can ignore this one. So distribution will become mj star equal to gj e to the power minus alpha, e to the power minus beta, epsilon j dash, which is called Boltzmann distribution. So the statement 1 says at very low temperature, Fermi Dirac statistics and Bose-Einstein statistics are distinct or different, which is true, which we already saw now. And statement 2 says at high temperature, there is no difference between Fermi Dirac statistics and Bose-Einstein statistics, giving the Boltzmann limit. This is also true, which we saw that at high temperature both are converges to both make a limiting case, which is called Boltzmann limit, or this equation is called Boltzmann distribution. So this is also true statement. So both statements are true, which is option B. So today we will see problems till here only. So in this course, what we have studied, we have done the, you can say, recapitulation of this basic compressible flow in the beginning, which talks about shock wave, normal shock, oblique shock, expansion fan, nozzle flow, and we have also studied basic thermodynamics, its laws, and some tensor notation. And we have studied hypersonic similarity parameter, Newton's law, properties of supersonic and hypersonic flow, perfect gas equation, equilibrium flow, non-equilibrium flow, Trojan flow, most probable distribution, chemical and vibrational, non-equilibrium, kinetic theory of gas, inviscid, viscous, high temperature flow, high temperature equilibrium flow or non-equilibrium flow. Chemically reacting gas mixture. And kinetic transport properties. And computational aspects. Of high-speed flow. These are the some of the topics which we have studied. There are some more topics, and these all topics were in very details, like this chemical and non-equilibrium flow. In which we all discuss high temperature equilibrium and non-equilibrium flow. These were in very detail we have studied. And so today is the last live session, and after this you will have an exam also. So best of luck for all of you for the exam, and thank you for watching the lecture.